All right, everyone. 4 o'clock. 4 o'clock. We'll go live. So, first things first. Tomas has an announcement he wants to make. So listen up.
Yeah. Okay. First of all, my exam review is going to be on Tuesday from 7 p.m. to 9 p.m. I realize a bunch of you, because of I think the conflict was 2:30, have the exam at that time. So what I did was I'm not entirely done with the exam review. I'm like mostly done. I printed out a bunch of drafts of what I have so far, and so I can also only take one though if you're going to be taking it on Tuesday, because I only got so many. Also, the printer in the LRC, they're like 10 minutes ago, it broke as I was trying to print them, so I only have 7 copies. Is it okay if I leave during class to print out the rest?
Sure.
Okay, so yeah, hopefully I can fix that. And, but yeah, in addition, I'll be at Woo 3rd floor tomorrow from 4 to 6. These are like sort of like fake office hours, if like, so because like I want to be able to like, also I don't have the answer key yet because I have to write that before tomorrow. But by then I'll have the answer key, and I also like know the answer. So I'll figure out which room it is, by the way, and send that out. I'll send this out on Piazza. 4 p.m. to, yeah, that doesn't overlap too much. 6 p.m. This is on Thursday, on Tuesday. So the idea is like you guys can have a try at it with the worksheets I have, and if you have any questions, first of all you can email me. My email is on the first page, or you can come to this thing. I'll be just chilling in one of the rooms, and you guys know Woo 3rd floor, right? Yeah, and but if you're taking the exam on Thursday, please come to the actual exam review. It'll be fun. Yeah.
Thank you. All right, so a couple other administrative stuff. I think I'm going to have you guys vote on a couple things now. So a couple people have asked if it's possible for you guys to bring a cheat sheet to the exam. Doesn't particularly make it that much easier, but I know that it's a little like a comfort blanket or something for all of you. So anyone want a cheat sheet? So who wants one? Like who would bring one? All right. Okay. I'll do this. One page. You can have it printed if you want, but don't go crazy with that. And I will say it will not help that much. Okay. I want to say that to make sure everyone knows that this is not the type of exam where there's memorization. Not the type of exam where I want you to be looking at your note. You're going to have to be working on the problem. Don't be like flipping through your notes, wasting time on that. Okay. But sure, you can bring a sheet. Yeah.
One page, one side.
2 sides. Sure. Really, you should not have much on it. Okay. There's a few things if you want to have like runtimes of common algorithms or some stuff like that. That's fine. It could help you a little bit, but not very much. Okay. Cool. Also, we currently are planning on having a discussion on Friday. 2 options. 1, we don't. Okay, hold your applause. Don't applaud less of this class. Option 2, we do something interesting. So I pick a special interest topic. I know some people aren't going to be here on Friday, and yeah, but I pick some interesting topic for us to do. So raise your hand if you want an interesting topic. Okay, and raise your hand if you want a day off. Okay. See, a day off for you guys doesn't mean a day off for me too, which is compelling. I will think on that. I'll think on that one. That seems like roughly split. I do want people to have the opportunity to do something interesting, but I also want to go one way or the other. I want it mandatory or not. You know what I mean? Anyway. Okay, and last thing, I have my office hours scheduled on Friday still also, but I can't imagine a lot of people are going to go to the office hours on the Friday night before break. Who would attend office hours if I kept them on Friday? Okay, maybe not enough people to justify it for me. Okay, how about if I did them after class today? Who would go to that, like as exam review? Okay, like just moving my office hours to after school today, and then you can, or after class today, and you can decide what. That seems like more people. I'll hang around here for at least a little while. If people don't end up actually staying, then I'm going home. But yeah, I'll do some exam review after class. Yeah.
Oh, that reminded me. In case you haven't guessed, my normal review session on Thursday at 7 is canceled.
Cool, cool. I think we also have office hours for the TAs. I think all of them are planning on doing them a little bit early. Who here is taking the makeup, by the way? Okay. All right, cool, cool. Man, so many. Okay, yeah, that's tomorrow, Tuesday, 7 to 9. Chloe's in charge of that. Do you guys know the room yet? No. Okay, look out for that. She should message you tonight. If not, I will get on top of that, I guess. But if you don't know by like late tonight, let me know, and I'll book us a room just quickly to make sure we have one. But Chloe's supposed to be on top of that. Okay, cool. All right, so today we're going to do exam review, basically, but we are going to talk about one new topic a little bit. First off, I just want to review a little bit of flow, just make sure that we're good on that. Okay, can someone explain flow to me real quick? Anyone? What's the deal with flow? Yeah. Yep, so we have some directed, connected graph. We're going to assume connected for all of our things just because it makes it easy. It is possible, by the way, unconnected would mean I have some other node that has no connection to any of these. We're going to assume that none of those exist in our network flow just because it is annoying to deal with. But they could exist. They're not banned in the network flow construction. They have some amount of flow, some amount of capacity along each of these edges, and we want to maximize the flow going from S to T. And the reason that we need specialized algorithms for this, rather than just saying maximize them as much as we can and maybe find paths and repeatedly add them, is the fact that they can in fact block each other. So we can block out some possible pathways to send flow by maximizing other pathways. Okay? And the way that we end up using flow, one of the main things that we do with it is that we convert problems into it. We want to construct a graph like this somehow such that finding the max flow tells us some solution to a different problem. Any examples of this? Yeah.
The last lab.
Exactly, last discussion. Oh, by the way, I forgot this. I bought a whole big bag of candy and stuff with my own money, by the way, so appreciate it. You're getting it first because you answered this. If you don't want to be tossing them, so just take one. If you don't want to be tossing them, give it to someone else who does. Okay? Yeah. Yes, right. Just throw the whole bag. Here. Yeah. Cool. There you go. Oh. You guys had a fight? Here you go. Alright, cool. Yeah, but when people are answering stuff, I got the good stuff, by the way, this time. Is anyone allergic to peanuts, actually? Ooh, good roll. Okay, cool. Yeah, so don't worry about that then. Okay. So, what we did in lab, can anyone tell me, so the problem was, we have two kids who don't want to share any roads or intersections in their paths. That is, we want two disjoint paths. We're given a graph, basically. We're given a roadways, and we want to find some route to their home or to their school from their home that don't overlap at all, either either on a road or at an intersection. So, to do this, remember all that we have control over with this graph is the connections and the capacities. That's all we have the ability to change with the network flow. And in general, when we're taking a problem and making it of a form of a different problem, or the input to a different problem, we want to keep that in a format that is solvable by our known algorithm. That's sort of the main point of doing this, is I have a very nice max flow algorithm. So I want to take some problem, convert it into an input for some known problem, a problem with a known solution, and then solve it. Now, with this, there were a few constraints. So firstly, we couldn't share a road. How did we have that constraint in here? So all the edges have capacity 1. But then we had the problem that none of the vertices, none of the intersections can be used by both of the kids. And how did we deal with that? Very nice. Anyone else? Okay, sure. Over here. So exactly, we had, for every one of our nodes with multiple inputs, multiple outputs, we would create 2 nodes such that they had a connection between them with capacity 1. So by doing this, we are artificially restricting each node to only have one possible capacity. So you see here the sort of the clever design of what we do is that we take our constraints of our original problem and we somehow convert them into constraints on the input to this problem. This is a general format of how we're going to do what you might have heard in the discussions called a reduction. We'll talk about that much more later, and you don't need to know that terminology, but if you're interested in it, you can look it up. It's basically where we convert one problem into another. So we want to convert all the constraints. We had one additional possible constraint, which was, in the original thing, I basically assumed that every road was one directional. And in fact, for network flow, that is actually an assumption. A network flow is only valid if all the edges are single directional, meaning I can't have an edge going backwards. This edge would not be allowed no matter what its capacity is. So if I wanted to add bidirectionality, anyone who got the bonus want to tell me how they did that? If no one else is willing to. Okay, yeah.
I did largely
Mm-hmm.
two directed.
So were you ending up with edges going both directions from any nodes? So you aren't allowed to do that. So I mean, if I wanted to do it so you can see first off that even if I just added a connection here, if I just added this, added one capacity edge over here, this actually wouldn't work, because you could have one go one way, one go the other way, and they'd use the same street. I'm not saying that's your solution necessarily. I actually don't 100% know what your solution was. Yeah?
If you could divide like each node.
Yeah. So the rough solution. I'm just going to sketch it. I think it's not worth writing down for everyone, but I want you to think about it. Is basically you can have the ability for the out node to go to the in node through a bottleneck. So you want a one-directional bottleneck, right? So you still need that one-directional bottleneck, but you can have all of the outputs go to the input, or any of the inputs go to the output, but they both have to go through this bottleneck. Okay. So you basically add an edge from the end to the beginning, but it has to go through the bottleneck. And then vice versa, also going through the bottleneck. That make sense? If it doesn't quite make sense, that's okay. Think about it on your own. Think of it as a problem. This is the sort of thing I might ask you on the exam. I won't ask that exact problem because some people have already solved it, but I could ask you something like that, okay? So treat that as a practice problem, and I won't give you the solution right now. Okay? If anyone wants a solution, stay for office hours. How about that? Okay. Cool. Everyone, any other questions on flow? So this is the general setup of flow. And remember, we had 2 algorithms that we talked about so far that could solve max flow. So we had, what were the names of those? Nope. Kruskal is minimum spanning tree. Utkarsh. Ford Fulkerson and Edmund Karp. Okay. Ford Fulkerson is sort of the default, like naive algorithm, which uses the residual. And Edmund Karp, what is the distinction between Edmund Karp and Ford Fulkerson? I mean, yes, that's the difference algorithmically. A little bit more intuitively, what's the difference? So in Ford Fulkerson, we take our original graph with its capacities and its flows, and we transform it into a residual graph. I'll call on you in a second. And we transform it into a residual graph, and then we find some path from the start node to the sink node, that's the S to T, and then along that path, whatever the minimum possible flow change, remember the residual contains all ways that I could modify the flow. We find some path from S to T, and that will be some way I can modify the flow such that I'm adding flow equal to the minimum possible flow change along that path. Does everyone recall this? If people don't recall this enough, I'll do an example on the board, but if people do remember it, okay. Well, we'll talk about it in a second then. Before I talk about residuals though, I'll real quick just say, does anyone remember Ford Fulkerson? What was the runtime? Did your hand for that?
Yeah, oh, I was just gonna say
Yeah, so we found that for Fulkerson, we used some way to find an arbitrary path, which DFS is a reasonable one for that. So we can use DFS to find that. Edmund Karp finds always the shortest path. That's the intuitive flip. And to find the shortest path, it turns out BFS will always return a shortest path. So by using BFS, we can guarantee that, and BFS is a known algorithm, so I don't need to re-implement anything, which is nice. Yeah.
Is this for the runtime question?
Sure, runtime.
Ford Fulkerson is O of E squared, and Edmund.
No. Sorry, those aren't correct. Yeah.
E times the maximum.
So Ford Fulkerson is E times the maximum flow. Very nice. E times the maximum flow. Why is that the upper bound runtime? Why is it times the maximum flow? That seems like a weird thing to have in my runtime. Yeah. Yep. So basically, because I'm choosing an arbitrary path in my residual, there are actual examples of this, which we did in class. You could always add one flow. Each residual that you add could add one flow. So we have to do it that many times. And each time we find a path, each time we run DFS, takes O of E time. It takes O of V plus E. That's how long DFS takes. So we multiply them. Okay, Edmund Karp, how long is it? Yeah. It's OVE squared. This one is a lot harder to prove, but the basic idea of it is that we know that as we saturate an edge, it requires a longer path to unsaturate it. Every time we update something using the residual, every time we do an augmenting path step, we will saturate one, and at most each edge can be saturated V over 2 times. Put all three of those facts together, and you get that it will, and you get that the algorithm will be run at most V times E times, and each one of them will take O of E time, right? If you don't recall that entire proof, rewatch the lecture if you'd like to, or try to rederive it yourself. Okay. How do we feel on flow? Okay, I'll talk about the residuals just quickly, just to make sure that we understand it. The idea of it is that every single edge in our network will have some flow and some capacity, right? So we'll have some node, and it'll have some flow and some capacity. And if I want to describe every possible way that I can change this, or the maximum ways that I could change this flow, we say that the maximum amount of flow that I could add forward is what? It would be C minus F. I would fill up all the capacity. That's how much more capacity I have left to fill. And how much flow could I no longer send across it? How much flow could I remove? F, exactly. So if I transform every edge from this into this, that will give me my residual. And my residual just contains all the information of all the ways that I could update my flow. And it turns out, we proved this in class, but you can work on it on your own if you'd like, that if there's a path from S to T in the residual, then there is some way that I can increase the flow, even if that means removing flow from some edges. And it also turns out that if there is more flow to add, then there will be a path in the residual. So between those two things, we know that repeatedly adding paths in the residual will give us a maximum flow. You can put those together logically. Okay? Everyone happy with that? Are you happy with that?
sort of.
Okay, cool. Well, any last questions on flow? Okay, yeah. Can we have non-integer capacities? Hypothetically, yes, but it ruins runtimes. For max flow, it will no longer be F max. If we allow an arbitrarily small thing, then it will be maximum flow divided by that arbitrarily small thing. So we could get a really, really bad runtime. We have to be careful. In general, in the formulation of network flow, we're going to assume integers. You can assume arbitrarily large integers, but we're going to assume integers. Yeah, if you want to add precision, just add to like the value. Yeah. Okay. Any other questions? Yeah, it's stuff about precision. We're going to skirt around in this class kind of a lot. Like what happens if I treat it as a floating point value instead of an integer and stuff like this. But most of them you can reason out on your own, honestly. It adds extra complexity to all the explanations. Okay, any other questions on flow? Can't have negative flow, can't have negative capacity? Yeah.
Are we gonna have to code out the flow algorithm?
The test is not going to have you do any, you're not going to have to do anything that we have done in class or anything that you will know the solution to ahead of time. So I will say, sort of directly referencing this, if you are asked to design an algorithm such that you could use max flow to finish your algorithm, you're allowed to say, and I use Edmund Karp or and I use Ford Fulkerson to complete your algorithm. You don't need to re-implement them if you're using that algorithm. Yeah.
Can you just re-explain
V squared, honestly, it's sort of a long explanation. I don't think I'm going to get it across in a time that is reasonable for this review. Rewatch the lecture. I go through it very thoroughly there, and you should hopefully be able to get it from that. But you can just, the lemmas that I just said out loud are enough to get this, to argue this. It just requires a little bit of cleverness in the proof. But I don't think it's worth the time right now. Yeah. Okay, yeah, the broader thing to take away from that, by the way, in terms of your own skills, is how to structure a proof, how to do a proof, rather than that proof in particular. That proof in particular, again, you do not need to memorize stuff for this class. Cool? Yeah. Cheat sheet double-sided is fine. Yeah. Don't, and I will look at you directly for this one, don't go insane with the amount that you write on it, though, because you're going to need to use it to read stuff, or you're going to get distracted looking at it instead of writing your answers. And I promise you that is a hindrance. That will not be a benefit. I have seen people write incredibly small, fill out a whole sheet double-sided, and then spend the entire exam squinting at it trying to read it. So don't do that. Okay. Any last questions on flow? Will the exam results be curved? They are curved by the attendance grade that you're getting, if that makes sense. Okay, I'll explain the pedagogy here for a second. You're getting 30% basically free points to the class. A big reason to do that is that I'm allowed to make the exams harder. Because now, like, I'm boosting it sort of by you all having that. So realistically, just to be honest, the average of the score of this exam is going to probably be lower than the average score of another class. That's not to say the test will be harder, but I'll be more honest about the feedback, probably. That said, my goal for the class, my expectation for the class, is that we have a mean around 85% at the end of the semester and a variance around 10. So almost everyone will be in the range 75 to 95. That's my expectation for the class. I may skew it slightly higher since I know that this is a Bay State program class. But don't really worry about any sort of scaling stuff. I will do it implicitly, and if I feel like it's necessary, I'll do it. But I try my best to not do it so that you get your honest feedback and don't feel like, you know, oh, the curve is I have to rely on it and stuff like that. Think your curve is basically I'm giving a lot of free points. Everything else is nicer so that the exam can be harder. Cool? Cool. All right. All right, any last questions on flow in particular? Yeah. Yeah, I swapped it. I'm doing exam review today just because so many kids have the exam tomorrow, and I thought it would be unfair to do exam review on Wednesday. But we'll do them on Wednesday. And for the project, they are basically necessary. So I'd say even if you aren't here on Wednesday, watch that lecture online, everyone. It's going to be an important one for your project. Yeah. You don't need your optimal runtime for the first submission. The first submission is just did you attempt it, and if you make modifications and you optimize it over the course before the final submission, that's fine. Yeah. Okay. Cool. All right. So if there's no other questions, guess what? Guess what the coin says. But before you get moaned and groaned because we're not doing exam review. You've all asked, so many people have asked for a practice midterm. This is the closest thing you're going to get to an actual practice midterm. We're going to spend 30 minutes on this one. This is a proper, actual, like, these are questions that I could have very well asked you on the exam. So if you want to benchmark of how well you're prepared for it, this is it. Okay? So when you're ready, take this. I'm going to say 30 minutes, work on it totally alone. Okay? If you finish early, then maybe come talk to me. I can give you something else to work on. But this will be practice exam for you all, okay? Take it when you're ready.
Hi, Sean.
Yes.
You're gonna share the solution.
What?
You're gonna share the solution. You're so nice.
I was about to say no, so.
Oh, you're the best.
What? What's the capacity? Seems like one. By the way, I might give you slightly less than 30 minutes, but that is 30 minutes for these questions is the difficulty and time constraint that you should expect on the exam, roughly. Go ahead, you got it. Oh. Do it now. Okay, let's say we're going to stop at 4:50. It's going to be on time. Always one source, always one out. And always ones where I give you a hint of how to do it. Not required to. I encourage it. You'll have a hard time if you don't, generally. Not be 5 players on every team. You should all take a chance to look at our notes. missing a 2. So it's cool. It's a last word is just missing a 2. I told him this is about, it should take him about 30 minutes. Yeah, it's just a word, it's the word 2. I noticed the typo after I printed them and I just not.
Yeah, it's okay. I did that. I should do that on the too.
Algorithm for this, you can you have that's a part of the problem is what how do you return? Every edge will have a float assignment to it. I'll let you figure. You don't need to be you don't need to write pseudocode for that. You can just say you write it in text. It's fine. Okay, so that's 20 minutes. Wise, in terms of the exam, if you haven't completed one of the questions, then know that you'd be behind pace to finish the exam. For your own mental. I'm going to allow you now to discuss with your neighbors if you'd like, or you continue working alone if you prefer, for the next 10 minutes. We'll go over the answers after this. Alright, you don't have a trash can?
I really live far away. So I like well, actually, no. I was here after class before you came to this meeting. Like, it was made. I saw him hand you the tablet. I'm gonna check. I'll prove it if I.
No, not yet. I was trying to finish this other one. Yeah, it was like the coaches. I did reverse. I had the coaches first and the same thing.
I had the sort of having an extra speech with the weight of however many people I want. And then I have a node in between, and then the connection to the same theme.
I had like similar routes. I did source, connection 5 to each coach, and then they could read any one individual one to every single player they wanted. And they only had 5 to do that. And then they go into the yeah, they can't. They can give out 5 flows. So they can have like 100. They can have N connections in there's one thing like
That's like a general, this is a general rule, right? Is that S&T the directions there?
It's actually like.
Oh, like in general.
and then I got the runtime was O and
O of N times each bridge. You had to find the same particular.
I know, but I made it. Yeah, that's what. And then the end becomes that, and then it upper bounds everything else that you would be adding in the creating graph and returning graph matrix. So I just said it was upper bounded by every card. Yeah, I would. Is that right? You know the answers.
The answer is
What you did is you just added well, the number of nodes is going to be m plus n plus 2. Just by the active focus is that's just using
Because then I did it out, and then it like just gets me like when you add it up, it just gets me because I know what the adding is like. No. Like I got this, and then I was like, oh, upper bound. Because I got that like V was M plus N, E was N times N, and then we'll do it out.
oh, yeah.
And then the E is squared, and then you do it out. And then it's N times N. That's what I said.
No. I'm all over the place. Ignore me. Capital letters are always erased, right? And no? Okay.
Those two are arrays.
Man, wasn't it a variable?
Well, I did submit them.
No, I know.
You probably should have done that. I noticed after that these are maybe a little bit hard to find. Parts are starting on a little bit harder than supposed to be. Maybe a moderate to one. Wait. It is side by side. And no, that is something I didn't add. Oh, how is there a range? Because most uses then you'll go to the no, you never oh, I mean, I guess if anything else that would mean what? If they're yeah, exactly. The way your graph looks is close to correct, but what you're making it is I feel like I'm not You'll see.
Okay, that's half the bad.
I don't like blind love. I give blind love thumbs down. That sucks.
It's becoming instead of it's like oh wait, I see the number. That means there are I or less. There are I occurrences in the number. Less than yeah. If I give you a
Okay, that's 30 minutes. Sorry, 30 minutes. Remember, I said that roughly this would take 30 minutes in terms of the difficulty of the exam. I'm gonna amend my estimation and say actually the pseudocode problem is harder than I intended it actually, having looked at it. I removed variable names to make it more difficult, but I think that overstepped a little bit. Regardless, that sort of thing, being able to read pseudocode, figure out what's going on and what the runtime of it is a skill that I expect you to know. So that is something that you should practice if you're having a lot of trouble with it. But if it was just difficult, especially under a time constraint, then that's expected. It should be about that difficult. Anyway, let's go through the solutions now. Okay, so first one, the kickball one, is the more important one I think for you it's a very, this is almost exactly the difficulty for the exam, by the way. So like this sort of problem is you should expect something of this difficulty, of this sort of construction, where I make you design an algorithm and it's about this hard to make it. Anyone want to tell me what their setup is? Yeah. Yeah, so create a flow network, good.
add S and T.
Okay, so we just have two nodes S and T. I'm going to put one over here and one over here.
For every player that we have, I create a new node, like a new node.
Okay, so each player is one node. Let's put them in a line right here. Maybe we'll see what's going on. So each one of these is going to be a player. So these are, I think I said they're M players. M players here. Okay.
And then add an edge from S to each one of these.
Yep. Capacity 1 to each one of these. Cool.
Then,
What else?
Do the same thing for coaches.
Let's make another line of them here. So this is the N coaches. Five, good.
Accessing the player.
For each one of the coaches, we add the 5 edges that correspond to the 5 players that they want, like so. And what is the capacity along those edges? All of them are 1. Okay? So what we can see here.
I think each team can have 5 players, so the coaches can choose any.
Yep. So so the 5 constraints that each team can only have 5 players is captured here. The coach there will only flow from 5 different players to each coach. That's how the 5 constraint is written into here. And the 1 constraint being that each player can only be on 1 team is right here. Okay? And then the fact that we have sort of this binary of either they're on the team or they're not on the team is captured by the fact that all of these have capacity 1. So they're either attached to this coach, so they're either sending their flow to this coach, or they're sending it nowhere else. They're either not sending it there or sending it to that coach. Because they have a capacity 1, they can only send it to 1 coach also. Yeah? It is possible for a player to not be on a team. This is a more general thing for algorithm questions like this. Do not make any assumptions that are not on the page. I wrote out all of the assumptions that you should make. Everything else you cannot assume. If you want to clarify them, you can talk to me and I'll always tell you the answer. And if it doesn't give away the question. But yeah.
Will this question be any different if?
Yeah, so if the players also had a list, then you would probably choose the intersection. That's a very natural thing to do. So if each player also had that, then maybe I might do the intersection or something like that. Yeah?
But each coach may have.
No, so they won't have more than 5 flow in because the amount of flow they have out is at most 5 by the constraint of the
More than 5
flow.
flow in, but it's still not possible.
Yeah, they could have more than 5 edges. In fact,
But
they
only 5 will be set.
yeah. But only 5 of them will be saturated. Only 5 of them will be chosen. Yeah. You could do it either way. So if I flipped everything and then changed the direction of all the arrows, it would be equivalent. This is the reason I do it this way is actually because generally with this constraint, with this setup, this particular kind of solution to this particular kind of problem is called bipartite matching. If you want something to look into after class, look at search up bipartite matching and work on that. Yeah. So bipartite matching is going to be an important thing that Flow is very good at. So this problem, if you tried to just do it with some clever for loops and stuff, you probably would get it wrong, actually. But it's a very simple problem conceptually with max flow, which is one of the best use cases of max flow that we've seen so far. Yeah.
Wait, so how many?
So each coach can have up to m over n. Remember? So each one of them has at most m over n, but could have fewer than that. I didn't say that they had an exact number. I said they had at most m over n. Or I think I might say exact m over n. Yeah, exact m over n, but they can overlap with players.
Also,
Yeah.
n is less than 5.
There's a chance that the team has 0 players. Yeah.
That's allowed.
That's allowed. Not an assumption. I
I
never said it on there. So you shouldn't make that assumption. Yeah. Okay, cool. What if you forgot your question? Then you shouldn't ask it. Yeah. Yeah.
If we like didn't come up with this, but
Yeah, I mean, the more general answer to do we give partial credit is yes. But like I said earlier when I was talking about the scaling and all of this, I will try to give you accurate feedback. That is sort of the kind of feedback that you get on a technical interview or something like that. Where if it's wrong, I'm going to tell you it's wrong, and your grade will reflect that it is wrong. But I do want to give partial credit. Again, the whole idea of giving 30% to everyone for attendance is to give some amount of that. So if just mentally, if you were to get like a 60 on the exam, know that like you would have gotten higher in a different organization of this class. Okay, just for the mental. Any other questions on this? Yeah, you remember?
For the pseudocode,
Yep. Yeah. So
you don't have to write out Ford Focus.
you don't need to write out Ford Fulkerson at all. I will say that basically the best way to answer this question, so anytime that you are doing a pseudocode or you're trying to communicate your algorithm, it is most important that someone else is able to replicate it, more than that you are very extremely precise with all of your wording. That is sometimes important, but it's not particularly important on these exams or in this class. Making a drawing like this that is extremely clear is actually just about all you need to do. So drawing out your algorithm, particularly for max flow, this is not the case for everything, but for max flow in particular, just drawing out this picture, labeling everything, and then saying, I construct this graph, it takes so much time to construct, then I run a max flow algorithm, it takes such time to run, is sufficient. All right, so if you do that on the exam, I will give you full credit. Cool? Cool. I think hand went down here.
You need to write.
So for flow conversion problems, picture and a short explanation is sufficient, as long as it is totally clear what everything is and how you constructed this graph. Okay? For this in particular. For some algorithm, like if I asked you for a sorting algorithm, a picture usually will not be sufficient. You'll need to write out some amount of pseudocode for something like a sorting algorithm. Yeah.
Does that also apply to the homework?
The homework? Yeah, it's sufficient for the homework too. And the homework has a few more details that are like slightly more complicated than this, but it should be good. Yeah. Again, it's much more about clarity of explanation than it is about knowing the secret handshake of writing pseudocode. Being able to read pseudocode is important. Being able to write pseudocode is slightly less, but still important. But the most important thing is being able to communicate ideas and understand ideas, and understand algorithms. Okay? Cool. How about runtime? So first up, how long does it take to construct this graph? Not quite. Yeah? Not quite, that's exactly what he said. So it would be more accurate to call it m plus n. So essentially the number of edges is really what we're, so it's 1 per edge. Or not m plus n, sorry, not m plus n. It's going to be the number of edges. But the number of edges is not m times n. Sorry, I think that's sorry for the confusion. So it's E, it's going to be OV. So it's going to be totally dominated by OV because E is going to be strictly larger than M and N. Not actually, I guess, it will be.
So like the total will be like 2 plus n.
Yeah, we can, the total would be some, like if I wanted to be extremely precise, I would be very long because I would need to talk about like what it means to like read an integer of n digits. You know, like it's a lot of nitty gritty, but we can say OV. We can say OV to construct basically any graph ever. We can say is OV. But how many edges are there? Do you want to answer that question?
I have
Okay, fine. Different question first.
for writing out the algorithm,
In general, I'm going to, so you should at least explain it, but it becomes sort of nitty-gritty to get into the details of it. You can say my max flow returns some list of edges, each with an assigned flow or something like that. Sometimes you need to do that, sometimes you don't. In this one, you wouldn't. This one is pretty clear what it is. The assignment is just the edges here that have ones. So you can say that in just like one sentence. But sometimes it will require you to say something a little bit more complicated. Okay? How many edges? Yeah.
2n plus n.
2n plus m. So let's see. So each one of these has at most how many edges?
M over n.
So it's going to be m over n edges per, wow, it's dead. M over n, and there's going to be times n of the coaches, is going to be m edges here in the middle, then it's going to be plus n over here and plus m over there. So it's going to be plus n plus m. So it's going to be 2m plus n number of edges, okay? And what is the range of the possible flows, maximum flows of this network? Yeah. So yeah, so the max is easier to think about. If each one of these is maximized, then we'd have 5 times n, right? So the high range is 5n, and the low range happens when each of these are assigned to the exact same players, right? Meaning that one team, so at that point, only those players are chosen, which is going to be just m over n. M over n players are chosen. It could be lower if we have m is really low, but we're going to say that it's this. Okay, so that's the possible range for the max flow. You could argue that the lower bound is different, but I think this is a fine answer to have. So then, what's the runtime of the algorithm? Well, it depends. Which one of these is lower? Yeah? Yeah, so Ford Fulkerson would give us, I'm just going to call this n, so this is a normal thing to do is I'm just going to call this n, I'm going to call this m plus n. So the n times m plus n is going to be mn plus n squared, and Edmund Karp is going to be v, which is going to be n plus m, times the number of edges, which is this, squared, which is larger. So if you go through it, you can show that it's larger. So this is one of those cases where you have to be tricky because for Fulkerson, we have described as a worse algorithm several times. but in fact, it gives a better bound, right? Funnily enough, by the way, you can probably realize Edmund Karp also is bounded by this. Little thing to think about, but every augmenting path that we add will have at least one flow, so anything that uses augmenting paths through the residual would also be bounded by that. So we could accurately say that Edmund Karp is going to be, in fact, O of the minimum of these two, E times F max and VE squared. We just showed that it is also definitely lower than that. It's definitely upper bounded by that, but it still is upper bounded by this. Okay? So little side note there, but Edmund Karp is in fact better. It's just that this other bound that we got given is sometimes looser than this first bound that we found. Okay? Yeah.
I think in this question it's ambiguous.
Yeah, you can say something more complicated about the range. I'm not going to spend too much time on it, but there is something more sufficient you could say. I think saying something like this is reasonable. It won't come up on the exam. But the exam questions I've spent more time making. These I decided last minute I was going to give you some midterm review. They'll be more strictly formatted, where it'll have more exact answers. Yeah.
Why is the lower bound
Why is the lower bound m over n? That was an argument that, so it would be min m over n 5n. There is, yeah, the lower bound, I believe, is just, yeah, so the argument here is that every one of the coaches overlaps completely, right? I am just assuming this, by the way. I didn't actually solve this problem. And because of that, then only those players would be assigned to everything. Every other player would be dropped. So it's sort of like the minimum number of players that could be assigned is what I was going with. And it would be, the lower bound would be a longer expression. It would be a minimum of a bunch of things, actually. But this was just one of those options. That's easy to explain. Yeah.
Couldn't every coach only accept one player?
Yeah, so it could be that it could in fact be from the way I phrased it. Yeah, I think that would be one of the min cases. It would depend on the relationship between m and n. Yeah, because I made the number of them m over n, which is just for the runtime analysis niceness. That's one of the cases.
I didn't notice that.
Yeah. That's a constraint. Anyway. Don't worry too much about the lower bound thing. It was sort of a slightly sloppy question for me. It would be a minimum between a list of different things. You can figure out what those are if you think that it's good practice for you. Okay, how about the other one, the pseudocode question? So this one, did anyone feel confident that they figured out what the algorithm does? Yeah? What is it? What? So it in fact is a linear time sorting algorithm. Do you know which one? It's counting sort. So it's something that I've mentioned in class a few times, but I haven't actually explicitly given to you. This algorithm is in fact counting sort, which I think better than me, I'll explain what it is briefly, but if you're curious about counting sort, you can look it up online. What counting sort does is it assumes that every element in the array is an integer of value at most k. That's what the k is in the input. And it goes through and it counts all of those integers. So it counts how many occurrences of 1, how many occurrences of 2, etc., etc., etc. And then it produces a list that has all of those values just ordered in a row. So if I said that I had 5 1s and then 2 2s and 3 3s, then I know that my output is 1 1 1 1 1 2 2 3 3 3. This only works, we can only get linear time. Linear time is maybe it is fine to call it a linear time algorithm, but it relies on the maximum number of digits. The maximum value, the maximum integer value. It's a very famous sorting algorithm. Yeah. Any questions on that? Yeah.
If we didn't know the exact name, just like
You didn't need to know the name. What you would have needed to know is that it is sorting the array. Yeah. So the description, if you just wrote the phrase, it sorts the array, you probably would have gotten full points on the description, on the summary side. Yeah.
So I kind of guess I was doing the array, but I didn't understand what the array
I forget exactly what it does. Yeah. So that's you're constructing the output. You're constructing the output type. Yeah. You can. It's sort of a complex way to write what in code you'd probably be able to read easily. What I'm testing here is your ability to read somewhat archaic things. It is still valid code, all of this. Like you could actually derive, if you wrote it out in real code, you'd probably be able to read it actually. Yeah. Yeah, if you did that, you're fine. You'd at least get partial credit. Yeah. And we did see, so the runtime of this you should be able to have seen is just going to be all of the for loops. You just add up the amount of time in each one of these, and you'll see that it in fact is going to be the length of the first two arrays added together times k. Yeah.
Would you write like all of n, or would you say like all of max length of a length of b?
That's a fine way to write the second one. Yeah, because you could also say that the length of a is like I would use this notation of size of a. Yeah. Yeah. Okay.